Good afternoon, everybody. This presentation is developing classification and recommendation engines with Amazon EMR and Apache Spark with Zillow Group. My name is John Fritz. I'm the Senior Product Manager for Amazon EMR, and I'm joined with Jasjit Tind, who's a Senior Director, Data Science and Engineering at Zillow Group. Actually, by a quick show of hands, how many folks here are running Spark ML today? So a fair amount. How many of you guys are on Spark 2 or Spark 1? And then how many of you guys are running it on EMR? Okay, so good show of hands. So real quick, just the agenda for the session. We'll talk real quick about just Apache Spark and Spark ML. It might be a little bit of a refresher for some of you of why we see this being adopted as one of the frameworks of choice to run large-scale machine learning jobs and data science. And then a little bit of slides on running Spark ML on Amazon EMR, some ways to do that with low cost and some options that you have. Show a quick notebook just of a demo that goes back to some of the classification algorithms that were mentioned in previous slides, and then hand it over for about half the presentation for Zillow Group to talk about how they've built classification recommendation engines for their products. So, as many of you know, Spark over the last couple of years has been a de facto engine to use for running machine learning jobs and actually data processing in general. Many of you might have used Hadoop MapReduce before, and despite this being a massively parallel system, there were some limitations. And so we found people adopting Spark, customers using Spark on EMR, for the first reason from performance. So just like Hadoop MapReduce, it's massively parallel, but instead of, say, running multiple MapReduce jobs like you might have used for Mahout job, which are some machine learning libraries over MapReduce, or something like Hive, Spark uses a highly optimized DAG to more effectively create a query plan and does some also full stage code generation to make these queries and these machine learning jobs efficient. Also, Spark minimizes I/O a lot. With Hadoop, between map and reduce phases, you're dumping a lot to local disk. You're also shuffling things around between nodes. With Spark, you can cache your data set, it's called data frame, in memory and distributed around all the nodes in your cluster, and then run things over and over and over again for iterative processing. Also, Spark's partitioning aware. It won't shuffle data in between nodes unless it has to, which is different than some of the previous frameworks before. So, we've seen customers who are adopting Spark getting a large degree of performance versus some other older open source frameworks. But another main thing besides performance is Spark is just easier to use, and we found that it really, to some degree, speaks your language. Whether you're more proficient in, say, Scala or Python, or you want to write R, there's a really either native interface or a very tightly coupled library that allows you to write code in the language that you want, or UDFs or whatever, to go easily construct these jobs. But beyond that, typically machine learning is one part of maybe your data processing pipeline, but as you can see, you need to extract features, you need to clean up data, and that might be other parts in your processing pipeline. Spark really allows you to standardize everything onto one core framework versus before you might have used MapReduce and Storm and other different libraries together. Here, you have your Spark core, which is familiar framework for all these higher level libraries, and then you can run SQL, you can run streaming jobs, you can run MLlib, which is what we'll talk about today, or create graph databases. So besides having great performance and the ability to use a variety of different languages to construct jobs, obviously Spark is being adopted for machine learning because of the Spark ML libraries. They're built on top of the data frame API, so once again, this concept that permeates all of the different Spark architectures you can build, kind of a collection of columns like a relational table. But Spark ML has a bunch of libraries that make it easy to extract, transform, and select features out of these data frames, so easily transforming it into a way to create your vectors, and then has a variety of distributed algorithms for classification and regression, clustering, and collaborative filtering. It also has a couple of tools that make it easy to do model selection, and because it's scale out, you can try many different models at once on a cluster, and then in EMR's case, you can shut down the cluster when you're not using it. And then finally, it has the ML pipelines tool, which makes it easy to stitch all of these things together and save it and rerun it later, using it for testing and training as well. There's a couple of different groups of kind of feature extraction tools that Spark ML has. And this is just a small selection. There's, if you go into the Spark documentation, you'll see a full list of all the different things, ranging from, easily extracting words, normalizing features, easily scooping things up and creating vectors. And there's a lot of things out of the box where you can just use these libraries to manipulate the data that you've loaded, out of data frames into your machine learning jobs. And you really can get this data from anywhere. We see customers on EMR, leveraging a lot of S3 as your source of truth and data lake. But you might have customer data in many different data stores based on your use cases and your full architecture. And you can pull data out of DynamoDB with the recently open sourced EMR Hive DynamoDB connector. By using with Spark, you can pull data out of RDS. You can use the Spark Elasticsearch connector, stream data in from Amazon Kinesis or Apache Kafka. Use the Spark Redshift connector, or use EMRFS, which is EMR's library basically to interact with data in S3 to pull data out. But you can create data frames and enrich data from all of these and utilize data in these disparate sources to train and develop your machine learning models. This is just an example. You can have a variety of different training data. You create the feature vector using some of these tools, which is easy, and then create the models. So there's several classification models in Spark ML, logistic regression is a common one if your data set lends itself and is more simple. Oftentimes just trying out logistic regression and seeing how it fits is usually a good choice. But also decision trees as well, which they're easier to implement, they can be very efficient, they can handle both numeric and categorical attributes, and in some cases it deals a little bit better with, say, edge case data. And this is an example of working down the decision tree to see whether what you're trying to find is in the class or not. And then oftentimes, once it's done, then you'll have partitions to be able to then use in further downstream processes. So Spark ML can take, these are a variety of two of the many algorithms that are just there. You can just start using them, testing them, and seeing which ones might fit your models the best. But then building these pipelines and saving them also is easy. As I brought up before, there's the Spark ML pipelines API, where you can take a flow like this and save it, where you might start out with raw text. You're going to use the tokenizer to chop it up into words, then create your feature vectors, and then choose one of many models, in this case, in this diagram, logistic regression, and then fit that model, and then you have the fitted model. But you can then use the same pipeline for your testing phase, where you get your test data set, more raw text into vectors, and then run that same model you had before that was saved with the pipeline to create your predictions, and then see how the predictions have worked and whether you might want to change some things upstream or try out different models. And creating a pipeline really is that easy. In this case, you can see this is a simple pipeline with 3 components, and then you fit it and then get your predictions. But you can make far more robust pipelines. But the point here is that with this API, you can save fully fitted models and have a lot of interplay between creating them. There's a couple tools as well to train many different models, take chunks out of your test and your training data set, and kind of have Spark figure out what's the most accurate one to use. This cross-validator and the train validation split. They basically iterate through many different models, and they'll get the fitted models and evaluate the performance. And there's other ways to do this as well, but these are handy tools where if you don't have your own framework to go do so, you can leverage things that are native within Spark ML and get a lot of leverage out of that. So that was a little bit of background on Spark ML, and Jasjeet will go into a little bit more on some of the algorithms they use at Zillow to build out these classification and recommendation engines. But I want to switch gears a little bit to talk about how we see customers running these applications in the cloud. And we see many customers adopting Amazon EMR to do it for a couple main reasons surrounding on this slide. One is ease of use. So if you're spending all your time creating these models, investigating your data, you don't want to spend a lot of time configuring Spark. You don't want to spend a lot of time managing clusters, and you also don't want to deal with dependency mismatches, these sorts of things. So with EMR, within a couple clicks in the console, you can have a fully functioning Spark cluster ready to run whatever investigations you want to do within a couple of minutes, several minutes. So very easy to get it up and running, fully configured with dynamic allocation and notebooks, and you can just start writing whatever jobs you have against data in S3. But it's also low cost. You pay for what you use. If you're not actively running a machine learning model, why do you need to pay for the cluster? You don't. You can shut it down. So in EMR, and we'll talk about this in a minute, but decoupling storage and compute, you can spin a cluster up when you need it, process the data, and then shut it down when you're not using it. Open source variety is important. As many of you know, Spark code base is moving very, very fast. It's incredibly important to have the option to run the latest version as soon as possible after it comes out. You get new features, new improvements, oftentimes new improvements to things in Spark R and Spark ML. EMR has been shipping Spark very close after the open source GA. We were a couple days behind when Spark 2 went open source GA. It was available in EMR within a few days, and minor versions as well. So we're committed to delivering the latest and greatest Spark bits as soon as possible after they're open sourced GA, generally available. There's some management things behind the scenes, and replacing bad nodes and scaling, variety of security features ranging from encryption, and if all of the kind of automated defaults aren't meeting your use case, you also have root access can add on other libraries. Oftentimes we find that if you wanted to augment the Spark ML machine learning libraries, say with custom ones that you've written or third-party vendor libraries, you can bootstrap those on at cluster creation time and utilize them along with all of the bits and components that are packaged. We have a few notebooks. Jupyter is natively there, or sorry, Zeppelin is natively there, which was born out of the Apache ecosystem. It is a very tight integration with Spark. The latest version of Zeppelin has some interesting authentication features if you have multiple users logging in at once. But also you can interact with things like Hive and other components in the Hadoop ecosystem as well. So it's a very powerful notebook. You can save things to Git, you can save files, you can back the notebooks in S3. So there's a lot of interesting features with Zeppelin. But if you don't want to use Zeppelin, you can use via Bootstrap actions, install things like Jupyter or RStudio that can communicate with Spark, Jupyter with Apache Tori as well, we found works well. And we expose a lot of these Bootstrap actions on the AWS Big Data blog. And so I highly recommend taking a look. We had a blog post a couple of weeks back about installing RStudio and Sparkly R, which is the interface for Spark R, and some other things as well. We're constantly adding those things on. EMR runs Spark on Yarn. So for folks who are running Spark, not an EMR, say using standalone or Mesos mode, EMR uses Yarn. It plays nicely with a lot of the other Hadoop components, but also is really great for dynamic allocation of executors to where by default you can log in, start writing a job, and you don't have to worry about specifying the number of executors and did I specify enough RAM. EMR will utilize or Yarn will utilize as much as it can to spread out the executors to run whatever workloads you put in. Also, we have available the Spark UI. You can access it through the Resource Manager UI, basically click through, and if you're running in cluster mode, it'll proxy you to where the Spark driver is running. It's very, very useful. You can see the DAG of the job, executors kicking in, configuration settings at runtime. You can see if there's an error. Typically, it will bubble up the stack trace so you can see exactly what happened and quickly go either figure out what Yarn container log the error is in, or sometimes it even gives you, oftentimes actually gives you enough context to immediately know what the error was in your job. Also, historical jobs are available in the Spark history server, which is available on the master node as well. A couple tips and tricks for basically increasing performance and trying to reduce cost, which is an important kind of components when designing any big data architecture. The first is autoscaling. This feature shipped in EMR a couple weeks back, and we found that there's a variety of use cases for autoscaling. One is if you're resource constrained while running a job, programmatically add nodes up to a certain amount, and with Yarn dynamic allocation enabled for Spark, Spark will start using those extra nodes and putting executors on them and scale your job out. But on the flip side, also scaling the cluster down and not paying for it when nodes aren't being used. Like for instance, if you have a data scientist, you come in, you create a cluster, you run some things and then leave for a couple hours, that cluster's idle during that period of time. You can set auto-scaling policies to say, look, if this cluster's idle, at the end of the hourly boundary, because you've already paid for the hour, shrink things down in the background and kind of dynamically scale out when more work has been added. So there's some you can save some serious costs by doing that, but also increase performance by dealing with scaling. What EMR does and how it works is that we pump a bunch of metrics into CloudWatch based on Yarn, and actually we have a couple new ones, one on the Yarn percentage memory used, so 80% of my yarn capacity is used. It's a fraction of 2 yarn metric, so it's a custom one that we pump. And also just the containers pending. Yarn runs executors in yarn containers, and the ratio of the containers pending over running, it gives you a good indication of if you put on another node, would you be able to put anything on it? So you can utilize those 2 metrics, also a variety of other ones we push, or even custom metrics based on things that Spark, you have to figure out how to instrument and push it to CloudWatch, but EMR will take that information and behind the scenes create CloudWatch alarms and use application autoscaling to dynamically add and remove nodes. And actually in the console, under the cluster details page, you'll see the events of autoscaling events, so you can keep track of, so if you wonder, hey, why is my cluster 3 nodes? You can see the events that kind of said, hey, you should scale down now. One other thing to add is that we find customers leveraging Spot to save significant amounts on their processing jobs. For those of you who are not familiar, EC2 Spot is a way to bid on excess capacity. It's almost like a market where if you bid above the current market price, you get that instance. However, if the market price goes above what you bid, Spot will reclaim that instance back. So it's very good for workflows, and obviously Spark's a distributed system, so it can typically weather some nodes being taken away. And if you decoupled your storage and compute in S3, your whole cluster theoretically could go, you would just rerun the job, and your data set with all of your training data or test data or whatever you're making predictions from will be safe in S3. So today we see customers creating a lot of EMR clusters using Spot, typically for the task instance type, which doesn't have HDFS data node, although Spark doesn't heavily utilize HDFS, but just it's easier to scale out and scale in without having HDFS do any rebalancing. What we found is that customers, depending on the spot market price, might want to have, say, a variety of different instance types based on what's the cheapest spot price per GB RAM or core available, and can you just give us that? Or not know what AZ you want to launch in. Because spot prices differ in AZs, it could be that one availability zone is having a spot price spike while other ones are low, and it's sometimes hard to know exactly what AZ you should launch the cluster. So coming soon, we'll have the ability to, in EMR, you can specify a list of different instance types and different bid prices, and also a list of different AZs. So if you want to run a machine learning job at cost, EMR will do a lot of the lifting in the back end to figure out what is the cheapest AZ and the cheapest set of instance types to run to give you that cluster at the lowest possible cost. And then finally, once you've done a bunch of investigation, you've utilized the notebooks, you have a job that you like, it's time to take it out of your sandbox environment, put it into production. And there's a couple ways that we see customers leveraging the AWS ecosystem to go do this. The first and easiest one is using an EMR step. EMR is an API, our step API, and you can add a step which is a discrete unit of work. In this case, a Spark application. Under the hood, we'll use Spark submit and submit it to your cluster. And that's interacting with an EMR API. You specify where your jar is in S3. EMR will take the jar application, run it, and then write out whatever output you've specified in that. And that's easy. You can keep adding steps, and it'll execute them in sequence. And then when you're done, you can even have a step say, terminate my cluster when this is finished. Or when you create a cluster, run these steps and then terminate it. For more advanced use case around steps, you can use something like AWS Lambda and say, well, on this event, trigger running the step, trigger creating this cluster, and it could be time-based, it could be, new data comes into an S3 bucket, it's watching it, go launch the job and go run the job. For more advanced use cases around, say, creating DAGs of jobs or things like that, you can use AWS Data Pipeline, which is a service in AWS that can provision clusters, run many jobs, then shut down cluster and create new ones. You can create really complicated workflows building with both AWS services and jobs within those services. But we also see lots of customers leveraging things like Apache Airflow, which was open sourced by Airbnb, which is another robust scheduler, Luigi, or even Uzi on the cluster. You can choose to install Uzi on EMR and use Spark actions to create DAGs of jobs. So with that, I'll hand it over to Jasjit, who will talk a little bit how they leverage this technology at Zillow.
Thank you. Thanks. Hello, everybody. Thanks for the introduction. So my name is Jasjit Din, Senior Director of Data Science and Engineering at Zillow Group. And today, I will talk about recommendation systems at Zillow Group. So I'll first give an introduction on Zillow, and I'll go through some of the use cases related to recommendation systems. I'll go over a high-level architecture of our recommendation platform, and I'll spend most of our time on deep diving into our machine learning algorithms. I'll talk about our training and scoring pipeline, and then finally we'll talk about the evaluation metrics we look at to make sure our models are working properly. So Zillow Group is a conglomerate of various real estate sites, mobile applications, and some of them are here on the slide deck. Trulia, which started in 2005, was among the first to provide home-related data such as home facts, prior sale information, online to make it available for everybody. It was quite revolutionary at the time. You couldn't get this data easily publicly. Zillow, which started around the same time, was the first to provide home valuation model for free. It was really kind of the first time where you can just go to a home, look at a number and say, oh, this is how much I should buy this home for, or this is how much I should sell it for. Street Easy and Naked Apartments specialize in the New York City market, and they're the dominant players there. HotPads is among the leaders in rentals. Moretech provides loan pricing information for multiple lenders. Restly provides developer APIs for real estate data. And then Loop is doing something that I think will benefit all of us, which is about making the real estate transaction paperless. I'm sure many of you have gone through a real estate transaction. It's still a fairly painful process. So now we'll go into recommendation systems at Zillow Group. And here are some of the core use cases include email, where we sell recommended homes for sale and recommended homes for rent on email, personalized for a user. And then when you go to the home details page, say on Trulia or on Zillow, and you'll see similar homes, modules, and that's also a recommendation-based algorithms behind the scenes. Personalized search is about taking your explicit query and modifying that with an inferred query that we compute offline using machine learning algorithms so that everyone gets a personalized recommendations. On mobile, what we're doing is providing contextual and location-aware based recommendations via mobile app notifications. And on Zillow, we have a feature called home claims, where you can go and claim your home and you can go and update your facts directly. And in order to increase coverage there, we do predictions on who is the homeowner of every single home. And we also do predictions on who we think is going to be selling their home soon. We have algorithms around lender selection, and we have algorithms around similar photographs and similar videos. So here's our high-level architecture. At the top there are the recommendation APIs. There's a real-time scoring aspect of that as well, which I won't go through today, but maybe in another session. And on the right-hand side, you have property featurization, where you take properties and extract signal out of those properties and convert them to a feature space that our recommendation algorithm understands. And I'll go deep into that later on. Property aggregate features are features on a property but leverage additional data such as user signals. For example, there's a feature to determine how popular a property is, for example, using user signals. Wedge counting is a in-house built collaborative filtering algorithm, and we'll go into shortly. At the core of all of this, as John mentioned earlier, is our data lake, which is based on S3. All the data for our recommendation lives there. And then Zillow and Trulia, we have a lot of so-called legacy systems where there's Microsoft SQL Server, there's Redis, there's MySQL databases, and we need to get the data from these databases and put it into the cloud. So we have custom data collection systems to get the data into the cloud. And we actually have a nice blog article on how we do this on our data science blog, if you want to read later on. User profiles are about building user preferences so that we can recommend personalized content to users, and I'll talk about that. And ranking puts it all together. Ranking takes the user profiles, takes kind of collaborative filtering, takes property features, and puts it all together. Okay, so let's go deeper now. Okay, so the fundamental concept for all the recommendation APIs is defining what is a like and a dislike. And the goal here is we want to predict homes for a user using behavior of other similar users. And to explain that, let's take this example. So Spencer, the CEO of Zillow Group, really likes the $19 million home and the $22 million home. And Stan likes and Spencer doesn't like the $664,000 home, more modestly priced home. Stan likes the more modestly priced home, but doesn't like the $22 million home. So the goal here is to predict, does Stan like or does he dislike the $19 million home? And our definition of like is the user actively engaged with the property. And a dislike means the user didn't actively engage. So what does that mean? Look at the right there. The candidate set are all visits to a property where the timestamp is not equal to 0. 0 means the user never visited a property, and a timestamp means the user has at least one visit to the property. Now, we don't want to use visits set to 0 because that will highly skew the algorithms because most users don't visit most properties. And we also we define like by looking at, for example, the number of views, time spent on a property, the number of leads sent, number of saves, number of shares, and there's all certain thresholds to all of these, and these are constantly being learned as well. And now that we have the definition of like and dislike, so I'll first talk about our collaborative filtering. So wedge counting was invented by a really talented data scientist at Trulia, Joseph Kong. And that's his actually paper. It was submitted in the KDD Cup in 2011. It came up among the top algorithms. And let me go over that a little bit, what that is. So in wedge counting, the idea is to take common items and common users and figure out, and their interactions with the item that you're trying to predict on, in this case a property, and determine, and then compute these wedges. So you can see in the top left, UTG represents the target user, and ITG represents the targeted property we're trying to make a prediction on. So in our example, UTG would be Stan, and then ITG would be the $19 million home. And then IOT represents another item, and UOT represents another user. So in the first wedge, you see that UTG doesn't like IOT, and UOT doesn't like IoT, and UOT doesn't like IoT. So if you count these all up, there's actually 8 configurations. And taking an example in the previous slide, there's like the $19 million home. So there's 2 wedges. It's wedge number 3 and wedge number 5. In wedge number 3, Stan doesn't like the $22 million home. Spencer likes it, and Spencer likes the $19 million home. So you increment wedge 3 by 1. These are all counts. And then wedge 5 is Stan likes the modestly priced home. Spencer doesn't like it, and Spencer likes the $19 million home. So we increment wedge 5 by 1. And then there's 8 of these features, and you count them all up, and you actually notice there's actually 16 features, so there's actually 8 additional normalized features. So one of the challenges in recommendation systems is that very popular properties, let's say the White House, get a lot of engagement, and that skews your results. So what we do is you compute 8 additional wedge count features by dividing that by the degree product GFU and KI, which represents, GFU represents the number of users that have interacted with an item, and the target item represents the number of users that interacted with it. So you just multiply it and divide by that number. So you get a total of 16 features. And we use a gradient boosted classifier, which John went over briefly. And then what you do is you make a prediction on all the user and property pairs that you want to make prediction on. We filter, in order to reduce cost and compute time, we filter by top 10 zip codes and by a certain number of properties per user. So in our example, the goal again is the user ID is Stan and property ID is 19 million, and the features are on the right. So you create this data set, use the gradient boosted classifier to train your model, and then you score new user property pairs with that model. So now we'll move on to the user profile. And the user profile, again, represents the particular interests of every single user. And the key signals that we use include traffic data on our sites, what users are viewing and what their interactions, those events. And we use mobile app data, interactions with the app. And we also leverage the search queries. And just like in our Wedge counting algorithm, the labels are like and dislike, so there's 0 and 1. And each property we convert each property to a set of categorical features. So you can see on the right that, for example, bathroom, you have 0 bath, 0.5 bath, 1 bath, and so on. The price, you have the price there, it's 100K to 125K. So everything is categorical in nature, and so properties have 1,000 features. And they're either set to 0 or 1. So, properties either could be, if a property is a 2-bathroom, then it's not a 0 bath, 0.5 bath. Those will be set to 0. And as I mentioned before, on the bottom here, you have kind of the bedroom features. And this user profile specifically, this user likes, the scores are between 0 and 1. And this user likes a 2-bedroom and also likes 3 bedrooms, but doesn't like a studio, doesn't like a 1-bedroom. So your model, again, it's a gradient boosted classifier. Your model outputs these scores per user. And as I mentioned earlier, ranking puts this all together. And that's a major topic on its own, but I'll cover some important parts of that. Essentially, what we do is you take your property matrix, which are a set of categorical features, either 0 or 1, and you take your user vector, which are those preference scores for the same feature space, multiply together, and you essentially get a single score at the end. And there's also additional features, such as at the bottom there I have age decay, populated-based scores, quality scores, that are part of this feature set. But ultimately, it's a very simple operation to once you compute the user vector and do the featureization. Now, here's our training and scoring pipeline. And at a high level, what this is all about is taking raw signals and collecting that data, and filtering that data to what we care about, and creating the training and scoring data sets, then training your models, score your predictions, and then put it into some data store so you can actually surface those recommendations. So let's go into this a little bit further. So in the recommendation use case, there are 3 types of data sets. We have the user behavior, for example, what users are interacting with on your site, mobile app actions. So we have a custom event API that is invoked, and that data then gets pushed into a Kinesis stream. So and then it lands on S3 all in near real time. For the property data, public record data, which comes from the counties in general, we have a producer that pushes the data also into a Kinesis stream. And for listing data, a similar idea where we push that into a Kinesis stream. Then for the user behavior data, what we do is we use Spark EMR to filter that data to what we care about. A lot of events we don't care about. And we store it in our user store, which is Hive backed by S3. And there's also a Redis store which stores the reverse index, which is for the Wedge County algorithm, it's important that you need to look up all the users that interact with the property. So the key here is the property ID, and then you have a vector of users. So that's also computed. Then we use Spark EMR to generate the training data sets, taking the data from the user store, taking the data from listing data and the property data. And we create the training set, again, in Hive backed by S3. We then train our models in using Spark, those gradient boosted classifiers. We store them into S3. I heard about the key value, editable key value pairs on S3 that I think will be very useful because it'll allow us to easily find there's thousands, tens of thousands of models, so it allows us to kind of mark that with metadata. So I'm very excited about that feature that was announced this morning. Then we use Spark EMR to score and make those predictions, and that ends up into a Redis database. For offline evaluation, fairly common set of metrics we look at. We have a validation set where we optimize the hyperparameters, do the hyperparameter tuning, and then we have training and test data sets. It's essentially you go back in time, you take from today, the past weeks of data would be your test set, and the week before will be your training set, and then you keep going back in time as far as you want to go. And key metrics we look at, your standard precision, recall, and freshness is very important because we want to surface fresh listing predictions for users, and especially listings that have important key changes like this, such as the list price dropped or increased. So we want to make sure we look at how fresh our listings are. Are they 1 day old, 2 days old, things like that. And then coverage. We want to make sure to surface listings that might not have a lot of user interaction, but we want to surface those listings to users that are relevant. So future work, we are looking into building classifiers for the listing descriptions. There's a lot of interesting data in the descriptions and doing text mining around that. Looking at images and extracting signal out of images to make better predictions. And then also we're very excited about structured streaming on Spark, and to move that fairly fast batch is happening often, but we want to get to more of a real-time scenario. So we're very excited about that. Leveraging more signals, and then doing more around real-time scoring, using in-session behavior to make predictions. Thank you very much. There's our blog on the right side, so please check it out. And also we're hiring, so please come join us as well.
Take some questions?
We'll take some questions. There's no mic, I think.
We'll take some questions down here. Thanks, everybody, for your time.